So let's go over the reactions for amines now. There are just a few, not that many. Okay, so first of all, just a little bit about amines. There are a lot of reactions we have already done, okay, for amines, so I'm not covering them over here. So for example, the substitution reactions that we did with alkyl halides, just in the synthesis part also. Then there was also the reactions with carbonyls to form amines, and in amines we have done that already in carbonyls. And then the reaction with carboxylic acids to form amides, okay, or different kinds of derivatives to form amides. We've done these reactions already, so we are not covering them over here, but those are all reactions of amines also, okay. But right now I want to focus on something very specific for amines. So here the electrophilic reactions for aniline. Aniline is really an interesting kind of aromatic compounds. So back when we were doing aromaticity and all that, we learned that aromatic compounds behave a little bit differently. They do substitution only, and not any kind of addition reactions for all the alkenes, right? It's just a substitution. So the benzene ring itself is quite activated or deactivated depending on what kind of group is on the benzene ring. So here is an amine group. Amine group is a highly activating group, okay, for benzene. And so what happens is that if you take aniline and you treat that with bromine, you don't even need a catalyst, and you can do substitution reactions, okay. And look at that, you even get multiple substitutions, okay, with bromine on aniline, because it's highly activated. Phenol was the other compound that was highly activated, aromatic ring, and then aniline is also one of them, okay. So it's a small information, although if you're doing these kind of reactions, you have to know this. But if you forget to do this on an exam for me, it's okay. I will not penalize you, but still you should know that aniline is a highly activated ring. So a very unique reaction of amines is Hofmann elimination. Now this is an elimination reaction. So we've been doing elimination reactions from very early on, E1, E2, dehydration of alcohols to give us alkenes. So depending on what kind of substrate you had, you could either get the Zaitse's product, which is the more stable alkene, or you could get the Hofmann product, which is the less stable alkene. So we also learned to do Wittig reaction, which also gives us alkenes, and that's not picky about giving you Zaitse's product or Hofmann product. It gave you whatever you wanted, okay? So, I mean, you have a different ways of making alkenes. So Hofmann elimination is also a good way of making very specific alkene, and that is the Hofmann alkene, which is the less stable alkene. The other aspect of this is that you have a nitrogen group here, right? An amine group. NH2 groups are terrible leaving groups. We know that because NH2 minus is a very strong base. So it's a terrible leaving group. So in order to make an alkene, you need to make it a good leaving group. To make it a good leaving group, you can treat it with excess of methyl iodide. You can use any alkyl halide, but methyl iodide is the most common one used. So you use methyl iodide, and then you end up getting a quaternary salt. Now that quaternary salt is now a wonderful leaving group, okay? And so in order for it to leave, it needs to pick up a hydrogen. Remember, it's a 1,2 or an alpha beta elimination. So this hydrogen is more sterically hindered, so it does not get picked up. This one does, okay? And so this eliminates, giving us the Hofmann alkene. All right, so it's a very good way of making the less stable alkene. All right, so here is another example of this, where you can take an amine and then treat it with excess of methyl iodide, make it into a good leaving group, and see, you can get a mixture of product, but the major product is going to be the Hofmann product, okay, over here. So this is called Hofmann elimination. But the main reaction we are going to cover for amines is actually with nitrous acid. And nitrous acid is not something you've encountered before, so let's talk about that a little bit. So you make nitrous acid by treating sodium nitrite with either strong sulfuric acid or HCl, hydrochloric acid. So both of them are going to be concentrated acids. You treat them with sodium nitrite at very low temperature, and then you end up getting what is called nitrous acid. Okay, so it's called HNO2, you can write it that way, or HONO, which is also called HONO then. And this acid that you end up getting, okay, the HNO2, this is not very stable acid, okay, so which means that you generate it in situ and you use it up immediately. Okay, so you can't keep it, even for a few hours. So as soon as you make it, you have to use it, so you be ready for whatever you want, whatever kind of reaction you want to do, okay, which is where we are going now. But you generate it right then, and it's very easy to make. Okay, we do this in the lab all the time, so it's not very hard to make. So nitrous acid is generally used for either just as an acid, or it is used to generate a nitrosyl cation, which is also kind of common. But what we are going to do is very specific, okay, for the reaction. So first I'm going to deal with the reaction of nitrous acid with secondary and tertiary amines. Okay, so I'll start backwards. Instead of taking primary first, we'll deal with tertiary amines, because with tertiary amines, you don't really get any reaction on the amine at all. Okay, so you get this kind of a nitro. So remember I said it generates a nitroso cation, so you end up getting a nitroso substitution on the benzene ring, for example. Okay, and so you don't get, and the main thing is you don't get a reaction on the amine. Okay, that's the important thing, and that is tertiary amines. With secondary amines, you do get a reaction, but that also is just like a acid-base reaction, and that acid-base reaction is happening, of course, on the nitrogen, and that gives you N-nitrosoamines. Now, both of these compounds are pretty useless for us, okay? So this one, unless you're very specifically working on something like this, you don't really have much use for this, okay? So this compound generally not synthetically useful. This one is also, then nitrosamines are not synthetically useful, but they are studied for their toxicity, okay? And so there is a whole backstory of how it was determined that these compounds are toxic. So you have to look into food preservatives for that, okay? And so but in any case, these are very toxic compounds, and they can be generated in our own body depending on what kind of foods we eat, because remember, HCl is already in our stomach. Okay, so if you're eating amines, which we do, in proteins, and then if you're eating a lot of preserved food, processed food, then you can actually generate these compounds in your stomach. Okay, that's the backstory there. You can read more about it. Okay, but it's very interesting how it came about. And so these compounds are very toxic in the sense that they're potent carcinogens. And so we study them for that reason. Synthetically speaking, not useful. Okay, so synthetically speaking, only primary amines will be useful for this. So here is nitrous acid with primary amine. So what happens is that if you take a primary amine and you treat that with nitrous acid, you end up forming this kind of a compound, which is called a diazonium salt. So N2, okay? Now, when you have this N2 here, this is an excellent leaving group, okay? Because that's nitrogen, right? It's just ready to go, okay, from there. How does it go? So you can have either an SN2 reaction on this, or you can do elimination, okay? And so either way, it's going to go away. Now, we just talked about the fact just a few minutes ago that NH2 group is a terrible leaving group because it's a very strong base. So here we have now a way to make this into a great leaving group, okay? And you can also do substitution reactions. What we just did before with the Hoffman elimination was just elimination, okay? But now you can also do substitution reactions, which is awesome, because with an amine group, you cannot do substitutions directly because, as I said, NH2 is a terrible leaving group. Okay, but once you convert it into a great leaving group, Now everything is fine. Okay, this is something similar to what we did with alcohols. Okay, alcohols were not good leaving groups. Okay, and I know I'm sidetracking, but just want to show you, okay, how we can convert bad leaving groups into good leaving groups. Okay, and so you protonated that, and once you protonate that, you end up getting a good leaving group. Okay, so now you can do other stuff with it. So similarly here, you can convert, NH2 into a great leaving group, and that's called a diazonium salt. Okay, and these diazonium salts that we form, they're really very interesting. Okay, because it's not just for aliphatic compounds, you can also make them on aromatic compounds. And here it is, okay, on the aromatic compounds. And why am I so kind of excited about that? You can probably hear that in my voice. Okay, why is that so interesting? It is so interesting because NH2 group, first of all, terrible leaving group. Second thing, you cannot do substitution reactions on benzenes. Okay, normally you cannot. Like an SN2 reaction, very hard to do. If you do any substitution, you do electrophilic substitution, not nucleophilic substitution. So now what happens is that once you create this kind of a leaving group, now you can actually do SN2 substitutions on the benzene ring. Okay, big difference, electrophilic substitution versus nucleophilic. In a nucleophilic substitution, your leaving group has to go away. Okay, so here the leaving group is an amine, which itself is a terrible leaving group. So we're doing two things here in the process, right? So we're converting a bad leaving group into a good leaving group. And second of all, we're doing an SN2 reaction on benzene ring, which itself is amazing. Okay, so if you go back and look into the aromatic reactions, you will see that we did a lot of electrophilic substitution. And in the electrophilic substitutions, we were substituting hydrogens, okay, in there. We never substituted a functional group, okay, an OH or a Cl. I mean, whatever substitution we did, and I know we did a couple, those were not happy substitutions. You really need harsh conditions in order to do those. But now this substitution can be done quite easily. Okay, just like you would do any SN2 reaction, you can do these reactions. So which means the nitrous acid reaction with primary amines is really a very important reaction. Okay, so secondary, tertiary, not so much. So previous slide I showed you with the aliphatic amines, and here we have aromatic amines. So nitrous acid actually is used a lot more for aromatic amines than it is used for aliphatic, because it is harder to do substitutions on benzene rings. Okay, and that's why this is so useful here. So here are all the reactions, okay, that you can do on a benzene ring by substitution. So once you generate the diazonium salt, once that is done, now you can use whatever nucleophile you want, and you can do substitution. So look at all these compounds that you can make. Okay, so if you treat the diazonium salt with copper oxide, you can get a phenol. You can make, chlorinated, brominated, iodinated, fluorination on it. We have not done fluorination on benzene rings before, so but now you can. So here is all the different kind of halogenated benzenes you can get. Cyanide group we were not able to get on benzene ring, but now you can. And the last one is the most fun one, is to just get rid of the nitrogen. Okay, and you might wonder, like, why would I want to do that? And that is when you want to make very specific products in a very specific location, right? Ortho, meta, para, whatever it is you want to do, then after that you can get rid of it. Okay, otherwise previously we had no way of getting rid of an amine group, or any group for that matter. Okay, so but now you can. Okay. Some other things to mention here. Why would you want to make chlorobenzene using an amine? First of all, you don't really need to, because, right, you can make chlorobenzene just by doing chlorination on benzene. Okay, but this is a substitution reaction, and this is just to show you that it is possible to substitute chlorine for an amine group, which it itself is an amazing thing to do. Okay. So phenol we were able to make when we were doing phenols back in aromatic chemistry, but that was a very harsh condition, okay, in order to make phenol. But now it's a lot easier to make phenol using diazonium salts. So this is the lab synthesis for making phenol. Very easy to make. One other thing I want to mention here before I move on from here is all these reactions that I put stars on. These are called Sand-Mayer reactions. Okay, and so in this case you have a displacement of the amine group by chlorine, bromine, or cyano group. And Sand-Mayer was the one who actually did these reactions, so that's why they are known by his name. So what do we do with this? Okay, what we do with this is actually very specific kind of synthesis. So we are going to be back into aromatic compounds and chemistry again, okay, with all of these. So you have to know all of these reactions, by the way. Um, and also want to remind you, we did not make iodobenzene before, okay? We made chlorobenzene and bromobenzene, but these two were harder to make, okay? You have to use different kinds of acids for this instead of using the traditional, what we did, FeCl3, FeBr3, right, with chlorine and bromine. So anyhow, just to show you all the variety of reactions you can do with diazonium salt. So here is how the reactions work. Okay, so for example, here if you have an amine, okay, in this case, so here you treat it with sodium nitrite, you get the diazonium salt, and then you treat it with potassium iodide and you get the iodobenzene, and not iodo, but the nitro group on there too. So here, if you see this is an interesting one, okay, because here this is a meta position, okay, so the CH3 and the NH2, they are on the meta position to each other. So if you ordinarily wanted to make a fluorine, first of all, there is no easy way to make fluorinated benzene. This is the best way to make fluorinated benzene, okay, and then also to get a meta position on there, that's also interesting, because if you had fluorobenzene, fluoro group is actually going to be electron withdrawing, and it would be a meta director, and if it is, then you cannot do Fieldcraft alkylation, okay, with any kind of a deactivator on the benzene ring. So these kind of reactions are tough to do, okay? And so when you want to make this kind of a product, well, this is a good starting material, okay? And then here is to make a phenol, okay? So again, this is a para position, and then now you can, easily make a phenol if you had an amine group on there already, okay? So the synthetic value for diazonium salts is a lot, okay, and these might seem very simple because I have only started with simple stuff here, but there are many more qualities for this, or I should say applications. So here is a synthetic application for nitrous acid and amines. So for example, if you wanted to take toluene and make this compound in which you have bromine on the meta positions form the methyl group, this is not possible in a normal way, because if you take toluene and you brominate it, you will end up getting orthopara substitutions, because alkyl groups are generally orthopara directors. So in order to make what we want on the meta position, then we can actually use another synthesis. And I know it looks a little bit long, but the thing is, it doesn't matter. It at least gives us what we want, okay? And what we want is the meta positions for bromine from the methyl group. So you take toluene and you do nitration on that, followed by reduction to give the amine group. Once you have the amine group, now you can do bromination to give the two bromines that you want in the ortho position, because the amine group is more of an orthopara director, highly activating, okay, than methyl group. So because of that, the bromine will be on this location, okay? And remember here, the reason we got the amine here on this location is because the methyl group is an orthopara director, so we just isolate the para product, okay, from there. Anyway, back to the synthesis. So here then, once you have the bromines on there, now you just have to get rid of the amine group, which you can do by by treating it with nitrous acid and then removing that group. Okay, so now you have your product. So it was a little bit of a scenic route, but we got there. Okay, and so this is kind of an application that you can have with aromatic amines, especially if you're trying to get your groups in very specific locations. Another common reaction for diazonium salts is to do coupling reactions, okay? And these coupling reactions are extremely common in combining two rings, okay, two benzene rings together. So what you do is you take a diazonium salt, okay, so you take an amine, you create a diazonium salt, and when you take an activated benzene ring, something like phenol or toluene or aniline, another one, and then you react it with the diazonium salt, you don't get a substitution. You get what is called coupling. Okay, so the nitrogen has not gone anywhere, it is still there, but now it is joined together with the other benzene ring. So this reaction is going to be generally, of course, because the phenol is orthopara director, so it's going to be on the ortho or para position. And depending on what kind of coupling you're doing, just keep an idea for steric hindrance also as you're going through this. But otherwise, this is a nice coupling reaction. This is also a very good way of making dyes, and this is how artificial dyes were first synthesized. Coupling reactions are used a lot to make dyes. So for example, here is a dye, just a random dye that can be used, but this is a very typical structure, okay, for any kind of dye, which means if you look at this here, you have the diazonium coupling going on right here. You also have a polar group, an SO3H, which is a sulfonyl group. And sulfonyl groups are really good for binding, okay, with the polar fibers of wool or cotton. And you know how it is when we have clothes and you keep washing them, the color starts fading. So you want that linkage to be really good, okay, between the dye and the fiber so that the dye actually stays. So anyhow, this is a typical kind of a dye. So let's see how we can make this dye starting from benzene. Okay, so you start with, of course, benzene here, and you do the nitration and then reduction to get the amine group on there. After getting the amine group, you can do sulfonation in order to get the sulfonyl group on there. And again, remember, amine group is orthopara director. So this is what you get. Then you can treat with the acid, nitrous acid, in order to get the diazonium salt. Once you have the diazonium salt, then you can add this group. Okay, again, this has to be an activated ring. And so once you add over here, then you end up getting the coupling reaction going on at the ortho position. There is no para position, so only at the ortho position you will get the coupling. So it's a very common kind of a synthesis that you can do for dyes, okay, for diazonium salts. So here I've given you a couple problems that you might want to try out for amine reactions and very specifically for the diazonium salts, okay, and how to work with them. So try to do these series, okay, as best as you can. The answers, of course, are given on the next slide, but don't look at that first. So really, we did only 2 or 3 reactions over here. We did the Hofmann elimination, we did the diazonium salt coupling reactions, and then some aromatic synthesis on synthesizing, very specific kind of locations for certain groups. Okay, so that's it.